start. Everybody, we have the distinct pleasure to have with us Peter Hofstee. That's theoretical physics for the first degree, having 2 degrees in Caltech for writing parallel distributed software, and then turn architect. Chief achievements that you're probably familiar with is the synergistic processing elements of the cell broadband engine, and then also an architect for a parallel system based on the cell processor that achieved the sustained petaflop performance. So he's a distinguished lecturer, scientist, sorry, in IBM research, and a part-time professor at UW. So, Peter, thank you for being here.
So yeah, thanks very much for the invitation here. Really appreciate the opportunity. So, I went from a physicist to a computer architect to kind of a systems architect, and in my current job, one of the things I'm trying to do is I looked at big data systems for a while, and now with the big focus in IBM on what we call cognitive systems, really AI. I'm trying to help understand what we need to do for our systems in the future to make sure that we have both competitive systems and capabilities. So what I'll do here in the talk is I'm going to give you a very brief introduction to AI, just to cover the basics for those of you who may not be as familiar with it, and I am giving a little bit of my own spin on things there. Then I'm going to talk about the Power 9 hardware and work my way up to the Summit Supercomputer, one of the 2 Coral systems that IBM just delivered. And then I thought it might be fun as a kind of an exercise to see what would happen if you try to simulate some model of the human brain on that biggest computer that we have. And I think it actually turned out to be instructive in terms of understanding which aspects of the system limit you when you go to such very large problems. So first, artificial intelligence, and there are many ways to look at this, but I think most people would consider deep learning to be a specific machine learning technique, and machine learning to be one of the things that we do. That is basically, you can call it learning by example as opposed to learning from rules, which may be more similar to how we operate. So here's a typical machine learning pipeline, and so what you do there, and I'll go through an example that was kind of looking at that vision primarily, but it applies to other areas as well. But in vision, what you would typically do is you look at a problem. If you take a machine learning approach, you have a way to extract features from your problem, say your image. That gives you, of course, a new input set, and then you go through a classification run, which might be support for vector machines or clustering examples, or in the case of deep learning, you'll see stochastic gradient descent, basically, to generate an output. In the case of deep learning, I guess the most basic view of that is that instead of having human-defined features, you define a network, and in the simplest form, the network is of a very homogeneous nature, a bunch of fully connected layers, and through a mechanism like stochastic gradient descent, you end up with a set of weights for the different functions within that network, and that then defines the that defines your classifier and allows you to, to classify your inputs from there on. So the reason that deep learning has taken over from traditional machine learning, I think, is usually attributed to two factors. One of them is that with the rise of social media and the internet, we have a much larger set of examples to work from, right? So if your approach is fundamentally to learn from examples, it helps to have a lot of examples. And we're bringing, again, in the case of images, obviously we're bringing tons of images together in one place. And the other one is the advent of more specialized hardware, and usually this is GPUs that allow you to process all that data within a reasonable amount of time. And this is one popularity metric, so it's still growing fast. So as a particular example, there is an image classification benchmark, and I'll give you some more details in a few slides. But basically, with machine learning approaches, classifying things into 1,000 categories or so, you got as far as having a 26% error rate. Humans on that particular one, which I think includes like specific types of dogs, so not everybody knows all those dogs and can tell them perfectly apart. Humans end up with a 5% error rate. And actually, with machine learning, as of a few years ago, it got, with deep learning, it got down to 3%. So, looking in a little bit more detail at how image recognition was done in more of a machine learning kind of workflow. So what you would do is you would define features, and those could be things like corners or edges or other things. A good way to find those is to use convolutions. And I've shown a few solo edge detector kernels that if you involve that with the image, you basically end up with horizontal and vertical edges. And ideally, you would like for these features, to not be terribly noise sensitive, for example. So what you also tend to do is you take the image and you smooth it a number of times with a Laplacian operator, something like a smoothing kernel there. And you make sure that these features that you're looking for are stable at different scales of the image. And you do things like, of course, now you have a whole bunch of features. You're interested in the most salient ones, so you do things like picking maximum features. And then after you have that bag of features, after you've transformed your image into a bag of features, you do some kind of a clustering algorithm. And it can be k-means, it can be support vector machine, it can be all kinds of things to learn the relation between the features and the thing that you're trying to classify. Right? So this is basically what machine learning was before the advent of deep learning. So now, if you look at a modern deep learning network, actually, I would argue this is remarkably similar. So people have presented, and certainly initially deep learning appeared to be very different, from how it was done classically. But if you look at where they've now ended up, it is actually very similar. What you see is a whole bunch of convolutions, and so this one is actually very, very convolution heavy. All these little yellow bars there are convolutions. You have operations like averaging, which is a kind of smoothing operation. So you see this going essentially through different image scales here. The red ones just concatenate things together, so they don't really have much of a meaning. You see the green ones that pick maximum features, again, very similar to the one before. And then at the end, you see some fully connected layers, like the brown one over there, that do allow you to do things like logistic regression. sort of the equivalent of these classifying them. I think since then, the thing that is getting refined is these last ones in particular, where we go from just a single fully connected layer or a few to more fully connected layers at the end. And what you see here is here's that kind of where we got to with machine learning, the introduction of deep learning, and then the kind of networks that you see over here get you to that 3% kind of array. Now the big difference, of course, between this and the classical machine learning approach is that instead of in the classical machine learning approach where the kernels were chosen by the designer, says, okay, I think edges and corners and things like that are probably relevant to understand an image. The kernels themselves are learned in this case. And we'll talk a little bit about learning later on, but for now just remember that those kernels are not predefined by a human designer, but actually are found as a result of training on, for example, a labeled image data set. And what is interesting is that if you look at what kind of kernels you end up with when you train, it's actually fairly similar to the kinds of things that people have believed the first layers of your optical processing do, which is these Gabor filters. So this is a set of human-defined filters that are biologically inspired. And here is a set of filters that was learned, right? So when you have a particular neuron, you can get these images by picking a particular neuron, right? And saying, okay, well, what is the way to maximally excite this neuron, right? And then if you calculate that, then you might get an input like this. And you see that very much the same kinds of features occur. Now this was obviously black and white, and this was a color example. So there's an additional set there. And indeed, once you know that, it should not surprise you that in many cases a very reasonable approach to doing something with neural networks for images is to actually pick the first layers from some other pre-trained network and redo basically the clustering approach, right? The final fully connected data. So why might we need more of those fully connected layers? Well, it's one thing to understand, that something like this is a bicycle, recognizing things like wheels and particular features around the crank and the saddle, etc. Right? It's another thing to recognize that, well, arguably out of this set here, this is a bicycle and that is a bicycle, or this used to be a bicycle. These might be more accurately classified as tricycles, but it takes a whole lot more context than just the local features of these images to come to a classification of the images down below, right? So, I don't know this for a fact, but my guess would be that if you're trying to get into stuff like this, you probably need more of those fully connected layers at the end. And you may get closer to how our brain actually operates. All right, so the new picture then here, at least for the case of image classification, is that for machine learning, we have that pipeline. For deep learning, the feature extraction is replaced essentially with these convolutional layers, and which gives you the learned feature, and then you have some kind of a multi-layer network, typically fully connected. Even though, maybe a few years from now, just like we now feel that we understand this pretty well, and we can, relate this both to the biology and how we did things previously, maybe in a few years we'll have a similarly refined understanding of how these later layers work. So now I'm going to look a little bit more at this. Well, actually, I first have a bit of a remark about these convolutional layers and what it means for architecture. So I think a lot of the optimization that has been done for neural net type processing, is actually very applicable to those earlier layers where you do lots of convolutions, right? It basically comes down to accelerating matrix operations. GPUs are popular, FPGAs are popular, maybe right now more for inferencing than for training. That could change, and I'll get into that a little bit more in a bit. And then people are also building custom hardware to accelerate these kinds of networks. And for an example of that actually incorporates a number of these things below here, there was a recent IBM paper at the VLSI. So, what are the kinds of things that you do to optimize for this is, well, first of all, you pay attention to your floating point format. The, simplest way to do that is to go to, lower precision, like half precision, and the latest NVIDIA GPUs are an example. So, because multiplication is in practice sort of an area squared kind of operation, a double precision in a similar amount of chip resource that you can build a double precision floating point multiplier. You can have sort of a 4x4 array of 16-bit floats, right? So not surprisingly, that Summit Supercomputer that I'll talk about in a bit, it has 200 petaflops of double precision float, and it has almost 3.2 exaflops of half precision float. But actually, it goes beyond going to half precision. If you look at what the TPU people did, some Microsoft work, actually I believe this also applies to that IBM paper, is that you'll see people go beyond the IEEE format and make specific choices for how to present floating point numbers at lower precision that are good for these learning kind of examples. One of the ones that I'm studying myself is something that's being proposed by John Gustafsson in Singapore called POSITs, which are also known as third generation Numerals. In this representation, it has a number of interesting aspects. One of them is that it's more symmetrical than conventional floating point. So if you're trying to do things like tan-H functions or similar things, it works out well. And also the number of bits dedicated to the exponent and the mantissa is actually variable, which gives you some additional properties. And the third property of this, even though I think they're still struggling a little bit, whether this should be a part of the standard or not, is if you when IBM introduced the multiply add unit a long time ago in the early days of RISC, and John Koch and Bob Montoy who worked on that, we found that we could get a better answer by not doing a multiply and then rounding the result and then doing the add, but keeping a higher precision intermediate representation. Well, you can extend that idea to something like a dot product, and what it leads to is something that there's actually a few different shapes. In one case, the precision of both the inputs of the dot product and the output of the dot product might be the same precision, but the intermediate result might be much bigger. So for one dot product unit for POSITs that we built recently, we actually had a 512-bit intermediate representation for a 32-bit answer. ARM, with its recent dot product instructions, at least one variant of those, takes 8-bit input numbers and then accumulates them into a 32-bit answer. So that's another possibility. And then the last thing that I'll mention here is you'll hear people talk about tensor units. So actually when you look at, and an earlier talk mentioned that when you look at conventional processors and what the die area is allocated to, it's all about bringing the data to the machine gun in Luigi's terms. So it's all caches with a little bit of execution units. If you look at a modern GPU, the vast majority of resource is actually dedicated to register files. And a tensor unit, which is basically defining something like a matrix multiply as a primitive, allows you to pass argument between the different execution units without having to go back to the register file. So, saving precious energy particularly. Maybe in the future also those register files to be smaller. Okay, so now I'm going to focus on that last end, the deeper neural net. So with the fully connected layers, by definition, these are all-to-all. They're defined by the weights and by the transfer function. If the transfer function was linear, then actually a multi-layer neural network would be represented as a single-layer multi-network. So the interesting multi-layer networks have non-linear transfer functions, which also means that the optimization space ends up looking kind of like an egg crate, right? So when we do learning, we have some kind of a objective function. For example, you might have 1 million labeled images, and your current state of your network is going to predict a set of outcomes for each of those 1 million images, but you know what outcome you expect. And the difference between those basically gives you a gradient in something like this. And basically all that learning does here is you use a chain rule to compute the derivatives, and you do gradient descent on something like this. There's a couple of parameters that are meaningful. One of them, obviously, is the learning rate, which defines how big a step you take. So, if you take fairly big steps, then obviously in the end you're going to sort of oscillate around the minimum. If you take smaller steps towards the end, you'll be closer to an actual minimum. But you also have less chance of getting to a global minimum. So they've also introduced another concept or hyperparameter called momentum, which actually kind of carries you on over little humps to maybe closer to a global minimum. So that's really as much as I'm going to say about these things in general, and specifically, I know that there's a lot more to say. Earlier talk referred to neural nets with memory, LSTMs, RNNs, all that. It's interesting, but I don't have the time in this talk. So now I'm going to switch to looking at high-end systems for AI, and here's a couple of examples. So this here is HGX2, the latest optimized system from NVIDIA. So here you see the GPUs, and then you see some switch chips. Here you see the PCI connections between this stuff and a dual socket processor board there at the bottom. The thing that's really interesting here is this connection here. So you actually see 6 switch chips here connected to another 6 switch chips on the other side, that each connect to each of these switch chips, connects to each of the GPUs, and the bisection bandwidth here is 2.4 terabytes per second. And supposedly this is meant to allow you to take a large model and actually keep some of the weights on different sets of GPUs. So in the conventional approach to scaling out training of large programs, you actually keep all the weights on all the GPUs, and then you give batches of images to the GPUs to try to make a local estimate of how the grades work, and then you gather them up and you make a step, etc. But in this approach, you actually divide the model over the GPUs, which is helpful, but also introduces a lot of communication demand. This here is a picture of the TPU3, so the latest Google developed offering and chip. And even though I think some of these things here actually carry water rather than signals, it's pretty clear that there's a very heavy investment in interconnect in these racks as well. So perhaps we should have an expectation that this kind of thing matters. So now talking about that Summit supercomputer. So this is a 200 petaflop machine. I already mentioned that it's almost 16 times that number for half precision. And it just became the number one supercomputer in the world in June. So besides the GPUs, which are certainly key to delivering that flow performance, the Power 9 core is also key to integrating, or chip I should say, is key to integrating a machine like this. So in case you didn't know, the Power 9 processor is very optimized to work with accelerators. And you can see that by, not only have we invested in a Gen 4 PCI Express, a total of 48 lanes, so even though I think in this system there's basically 38 or so, maybe 40 that come out of the package. But so that's quite a bit of bandwidth over there, right? So 48 lanes PCI Gen 4 is actually 96, almost 100 gigabytes per second in each direction. And we also have these interfaces called NVLink, which NVIDIA usually uses, and for example in the HGX2 they use that to cluster the GPUs together at high speed. We've integrated that interface in our CPUs as well, actually starting with a variant of Power 8. So here you will see it's a total of 150 gigabytes per second of NVLink bandwidth, both leaving the chip and entering the chip. Now we wanted to make this available not only to GPUs, but also other things like FPGAs or communication adapters, or maybe getting to storage class memory or things like that. So we have an open interface that uses the same physical links in this chip called OpenCAPI. It's actually the third generation of the CAPI protocol that we now can run over this as well. The second generation of the protocol still runs on top of PCI. And it actually gives us, with OpenCAPI, so we can use that on 4 of the 6 links for historical reasons. And per link, we actually, I've seen some measurements out of our lab, we are able to achieve an actual data rate, useful data, out of that 25 gigabytes per second per link of 22 gigabytes per second, which is a very, very good fraction of peak bandwidth. So across those 4 OpenCAPI links, you also have about 100 gigabytes per second in each direction over this interface. And this is a shared memory interface, right? So accelerators, you don't have to take the data, and put it into a different address space or so on. The accelerators can operate directly on the memory attached to the processor. So the memory is attached at 170 gigabytes per second, but this is actually the total bandwidth, right? So over here it's 100 plus 100, here it's 170 total. So you are able to take all of your memory bandwidth and get it out, over this interface to the accelerators. And then in addition to these interfaces, we have some SMP interfaces as well, and these can also, maybe not so much in our dual socket systems, but in our scale-up kind of systems. We repurpose this stuff for our longer distance SMP links. So now, if we look at the node inside, this is actually the node as it looks like in the other of the 2 Coral supercomputers, Sierra. So we have 2 Power 9 processors. Actually, the memory that is configured in Coral is 256 gigabyte on each, but it could go up to a couple of terabytes in the node. And then, as I mentioned, six of these high bandwidth links in each Power 9 processor attached to the GPUs, and they're also interconnected in every link amongst each other. So, looking across this, it's 150 gigabytes per second in each direction while there, another 150 gigabytes per second over there. And then, in the particular way it's configured in the supercomputer, we actually have kind of a shared adapter that takes a by 8 from each socket and gives you 2 100 gigabit InfiniBand links. This is what these systems look like physically. oh yeah, I should have mentioned, in the Summit supercomputer, instead of having 2 GPUs, we have 3 GPUs. It's water-cooled instead of air-cooled. And then, of course, each GPU gets 2 of these things instead of 3 of those things. But that's basically the only difference. So here's what these systems physically look like. This is the water-cooled one. With the, these are the power processors. Here's the DIMMs. 1, 2, 3 GPUs there. 1, 2, 3 GPUs there. Here is this is actually a little bit funny. This isn't not the picture I showed. This is an air-cooled version, kind of this same architecture. And one thing you might notice is there's something going on here, because I know this audience is interested in FPGAs, so we digress just quickly. So if we take a close-up look of that, this is a little adapter called the Acorn card, which takes one of these NVLink/OpenCAPI interfaces, and actually, in this case, brings it to an FPGA. So this is an alpha data 93. It gets its power from the PCI slot, but it's connected into the system through this OpenCAPI interface. So through this, you can now get data into this card at 22 gigabytes per second. And actually, there's already cards beginning to show up that have, two of these connectors on a single FPGA card, and also this socket here. There are actually two of those interfaces that you can connect to. So we could put a system together where we replace the GPUs with FPGAs, and each of these FPGAs would have something in the order of 40 plus gigabytes per second coming in and out, and again, in a shared memory type architecture. And that, for a 2-socket system, you could have up to 8 of those interfaces for CAPI. In a 4-socket system, obviously still have more. So I mentioned earlier that FPGAs have been more popular for inferencing than learning. I think the next generation of FPGAs that are just beginning to sample now might change that, and that the reason is that one of the things that makes these GPUs so attractive for learning, besides the high floating point capability, is their high bandwidth memory. So we heard about about the memory stacks with the logic layer at the bottom. This is basically the same thing, but without that logic layer at the bottom. And then there's a piece of silicon that sits underneath all of this, and all these wires from these columns of DRAM are brought to the HBM. So one of these things gives you a couple of hundred gigabytes per second of bandwidth. In the GPUs, there's typically 4 of them. So you might have something like something approaching a terabyte per second, 800 gigabytes per second of memory bandwidth. These, I think, do 200, 250 gigabytes per second. In the FPGA, just in case you're wondering, this is exposed, I think, as 32 AXI interfaces to get to this HBM memory. So that means that from a bandwidth perspective, FPGAs are beginning to catch up with where the GPUs are. Okay, back to the Summit supercomputer. So I explained, the processor and the node to you, and well, I didn't explain the NVIDIA GPU. It's about 7 teraflops. This is again the double precision number, multiply that by 16, so you end up with 100 teraflops or so for precision. And assemble it into racks and into compute systems. So in summary, we have 4.6 thousand nodes, 2 Power 9 processors, 6 GPUs in each node, 200 gigabit InfiniBand, about 2.5 petabyte DRAM. So yeah, don't be confused by the previous picture. Here it says 10 petabyte, but that's the sum of DRAM and flash that is hanging off of each node. And about 200 petaflops, double 3.1 exaflop half precision. So for this exercise, I'm going to think of this as roughly 10,000 half nodes. So when I talk about a node in what follows, it's going to be a single power processor. It's 3 GPUs. Okay, so now for the model of the human brain. So we have a neuron which consists of a cell body and actually another synaptic interface here, the axon that carries the signal out, dendrites that take it through the destinations, and on the input side also some dendrites and synapses either on the cell body or on the end of dendrites that the outputs of other neurons connect to. So typically a neuron may have up to 10,000 or so of these inputs, and that is if you're still, I think if you're a 3-year-old or so. If you're my age, if you have half of that, you're lucky. A human brain has about 100 billion of them, and a range somewhere between 10 to the 14 or 10 to the 15 synapses. The maximum firing rate is 500 hertz, and so we'll do our simulation in 1 millisecond intervals. And actually the firing delay between the output of a neuron that this neuron fires into, so how quickly is it that something that this neuron fires causes another transition, appears to be in the order of 10 milliseconds. That might seem awfully slow for some of the things that we do, but actually there's a faster path for specialized neurons that I'm not going to get into, but not the majority of neurons are of this chemical type. So here's a brain-inspired circuit that IBM developed, including a number of people in my lab in Austin. It basically takes. So think of each of these as a neuron. These are dendritic outputs of other neurons. And each intersection here, if it's there, it represents a synapse. And in this particular case, you have a +1, 0, or -1 weight, depending on whether this is contributing or inhibiting firing. So it's being simulated in a little core like this. And for a chip that does about a million neurons, it only burns 63 milliwatts. So this, is an interesting thing to look at. Read the science paper if you want the details. So we take a similar such model. So again, 100 billion neurons, every intersection synapse, pulses. We will assume are fixed amplitude. If there's variation in that, we'll take care of that on the weight side. So we'll carry something like 4 bits instead of just the +1, 0, -1 for the synaptic weights. And there's this delay as well. So let's first look at bandwidth that this implies. And I would point out that this is sort of a very bandwidth optimized kind of architecture, right? Because a neuron either fires or it doesn't fire. So that's just carrying a single bit. So, if I took 100 billion neurons and a millisecond interval, I might end up with 100 terabit per second. But they only fire about once a second, so that means you have 1,000 in this. You have about, on average, 1,000 zeros before you have a 1. So you can do a run length compression and end up with about a factor of 100 less. So let's say a terabit per second. Which from the summit bisection bandwidth, that looks fine, right? No problem. But actually it's not fine, right? Because if I take an approach where I say, okay, I'm going to take these 100 billion neurons and I'm going to split it over my 10,000 path nodes, I end up with 10 million neurons per node, and it actually turns out that on average every other neuron needs to talk to each node, so it means that I have to get my terabit per second in over my 100 gigabit per second interface. Okay, so that's a problem. Now, actually it turns out that of course your brain has some structure, so there's roughly 10 layers in your cortex, and if we make a simplifying assumption that a layer talks to the next layer, etc. Which of course is not entirely accurate, but roughly accurate. Then essentially you have to solve just 1/10 of the problem, 1/10 of the machine, and that means that you now have to distribute the signals of only about 1/10 of the neurons to each node in the next layer, which gets you to that 100 gigabit per second rate that we actually have. So that's good. So now let's look at memory. So we have a total of 10 to the 14 to 10 to the 15 synapses, 10 to the 4th node, so 10 to 100 billion synapses per node. Per synapse, you know, if we keep them in a per target neuron list, we will need to encode the target neuron. We need 20 some bits for that, and the weights and delays say another 4 and 4 bits. So we need about 4 bytes per disk, which means that we, you know, in the 256 gigabytes per node that we have, you know, we can't quite get to the 10 to the 15, but we can get to about half. You know, which is still plenty to simulate my brain. So now let's look at memory bandwidth. And this is actually, this I think probably is the main limiting factor. So actually we cannot access memory at an arbitrary grammar, right? So you have to, you know, there's a burst rate in DRAMs, and memory interfaces tend to, you know, give you a minimum access granularity, which in the case of P9, this is actually half a cache line, but we can fetch half the cache line, which is 64 bytes. So we have, I know we have 170 gigabytes per second memory bandwidth. The effective bandwidth is more like 130, takes 64 bytes. So it gives you roughly 2 billion accesses per second. And if you look at what we actually need, you know, in terms of how many, you know, how many neurons are going to fire, you know, carry their information into this node, it was 1/10 of those 100 billion that each fire on average once a second. So that's 10 billion updates per second, which is, you know, 1/5. Sorry, 5 times larger than that. So this is a problem. You know, you can actually do something about that, because remember I mentioned that the you know, the delay between a spike from a neuron and when it causes the next neuron to spike is something in the order of 10 milliseconds. So it actually means that and if every spike is 2 milliseconds or so, you know, between the spike itself and reset, that 500 kilohertz signal, it means that in that 10 millisecond, you know, I can actually afford to look at a spike train, and instead of sending, if I have 5 spikes in a row, instead of sending 5 spikes, I could send 1. You know, it says, you know, this was repeated 5 times in the last 10 milliseconds. Right? And this would still work. Now, not everything is so perfectly balanced, but if it was, if everything was a train of 5 spikes, you know, I would have my 10 billion updates per second. And you know, you can think about other things like you know, keeping off and firing neurons in the GPUs instead of the CPUs. So now what we have is for every neuron that comes in, you know, we do this access. We'll have to go through some kind of a hashing structure and deliver a list of updates to the GPU. So at every list, you know, for the 10 to the 15, if we assume 10 to the 15 synapses, each of these lists is going to contain something like 10 updates, which means that the GPU is going to have to access its memory at 10 times the rate of the CPU. And furthermore, it's going to have to do a read and a write to update its neuron state. But fortunately, between the 3 GPUs and in this HBM memory, we have 2.4 terabytes of bandwidth, so we easily have that factor of 10 more bandwidth than we need. Okay. And then finally, the compute. Well, we have 10 to the 11th synapses per node, which, you know, if you need 1 flop, no, you may need more, but if you needed 1 flop to update a neuron with a synaptic firing, that'd be 100 gigaflops. We actually have like 100 teraflops of half-precision float in each node. So, you know, compute is not likely to be, you know, our problem at all. Or if you want to turn it around, you could have a much more sophisticated model, you know, to update a neuron than the single model you see here. All right, so it's actually some earlier work that did this. So we're across how fast it is and the number of neurons and synapses. This thought exercise here is about a factor of 100,000 better than that one from 2009. There's more recent work from 2011, which actually is quite impressive. It gets within a factor of 1,000 or so of what we surmise here. But this is actually simulating that true north a system consisting of many true north chips that I showed before. So it actually assumes quite a bit more locality than I'm assuming here. Within each of these orbital layers, I'm basically fully connected still. This looks like a pretty significant advance if you could actually pull it off. So in conclusion, it looks like you could get pretty close on to do this. So this might be worth this might be worth trying for real. The main reason I did it is I wanted to learn something about what actually limits you, when you go to these very large models. And clearly it wasn't the flops, right? Very much, network bandwidth. We got away with it. We just squeezed by, but only because we have this very efficient representation where the only thing that we have to carry for a neuron firing is 1 bit, the neuron fire. It goes a little bit at the expense of, more memory on the synaptic side. So, maybe we could have pushed that around a little bit differently. But in the end, where we ended up being limited was memory bandwidth, more than network bandwidth. But it was kind of close. Now, of course, this is a lot of power, right? So, it's one thing to be able to do this. You'd like to be able to do it in less than 10 milliwatt. And then the other hope that I have is, I know that I only briefly talked about FPGAs and open power systems, but I hope I piqued your interest there. So if you want to know more about this, let me know. By the way, these systems are not just IBM systems. There's maybe a dozen or so vendors that are building systems now with ARM processors that you could use to hook up FPGAs and all other accelerators too. All right, so that was it.
Questions?
Very interesting talk. We have done some work in the last few years with some neurobiologists to simulate parts of the brain, and they have these ultra-detailed models with profiles that they call AMBA and all sorts of things like that. And to make the long story short, we had a convey and we used all 4 FPGAs, full bandwidth of the memory, and we got up to something like 70 neurons, which was an order of magnitude more than they could do in a cluster, because from a certain point on, communication was just the limit. So the question is, having a more simplified version of it, of course we didn't have anything as fancy as what you have, but having a more simplified version of a neuron that just fires or has a spike, and maybe you can even cluster spikes, is it something which is very useful because it can solve real problems, or we need to look into this more detailed model that you have profiles and things that don't fire after they have fired for a while and so on?
Right. So I should preface my answer by saying that I'm not a neurobiologist, right? But the one thing I did briefly point out and I would emphasize is that the place where I was clearly not limited was compute, right? So if instead of doing a very simple kind of okay, this synapse fires and it dumps so much charge into that presynaptic part of the neuron. And that's it, and plus some leakage rate or something. Well, you have 1,000 flops or so available for every neuron update. So clearly you could, and that all happens within the GPU itself and between the GPU and its registers, right? So I don't know if you could do a sophisticated model as the one that you've been looking at, but clearly you could do a much more sophisticated there without actually changing the global communication structure.
In our case, because the interconnect was massive, essentially what we did was we used the DRAM to say who's connected to who else,
Right.
and we used the internal state of the FPGA to just tally up things on a per neuron basis.
Right. Yeah, which is basically the same thing here, right? I'm using the DRAM and the P9 to take an incoming thing that says a neuron 5 to then decide, what updates need to happen, which is basically the same thing. And then the GPU is just the actual update.
It would be entirely feasible to have a very large scale type of experiment on your system with.
It appears so. Yeah.
No, I'm sorry. Large, I don't mean just in terms of neurons. I'm talking about
in terms of model.
resolution and
Yeah,
model
yeah,
and.
yeah.
Yes,
Also,
that's huge.
I didn't mention, well, I had it on the chart, but I didn't say it. So each GPU has, between the three GPUs, we have something like 48 gigabytes. But we only have to hold the state of 10 million neurons there. So, that means that we have many several thousand bytes. So we have several thousand flops and several thousand bytes. For each neuron. So you could do pretty sophisticated models there.
And how accessible is your system to somebody who is?
Well, you have to talk to Oak Ridge, but this is at least for the time being, this is an open science system. So all you need to do is, I think, send a proposal to Oak Ridge for what you want to do, and if your proposal is ranked high enough, then it's not IBM system anymore. We've solved it.
Thank you very much.
I want to ask, is this the brain project? Is this some extent work for the true knot system?
No, this was just something I did in the last week, to prepare for the keynote. I thought, okay, what can I do that is a little different.
We actually trying to simulate the cortex size of neural networks, but we use a more complex model.
Right.
We use the millicolumns as the smallest.
Yes, and right, and clearly, you saw that I did get in trouble with the amount of memory that I need in each node, right? And that was a consequence of how much state I need to carry for each synaptic thing, right? And if you have like true north, right? If you have, just like I got myself a factor of 10 on global communication by assuming that the cortex is 10 layers, kind of like this. Of course, physically, if you have more of a columnar structure, and certainly if you look at pictures, there seems to be a lot of neurons that sort of run vertically, and then a few that come across horizontally. If you assume that kind of structure, then you could do that here. One reason that I think, so here I only talked about inferencing, right? So you know all the weights, and now I want to run the brain. However, I think when you're learning, right, you may want to start out with this kind of fully connected, more, I don't know, really needs to be fully connected, but more fully connected architecture, right? And then sort of morph your way into, learn your way towards not only the weights, but essentially the topology. So that is one reason I didn't want to too hastily, say, oh, well, I can solve this by also assuming some locality.
And also, do you think the propagation of the spikes is a bottleneck for this kind of system?
Yeah, so it turned, I guess the only way it turned out really to be the bottleneck. So when I started this, I actually the previous thing I had done was a sort on GPUs, and my conclusion was the network is the limiter. So I thought, let me do another problem and show that the network is the limiter, and argue for bigger networks on these things. Well, that didn't work out. Now the only So the one thing is that in order to reduce the number of updates, on the memory subsystem, I talked about these spike trains and the fact that if you know that the delay is something, you can handle more spikes at the same time. That does not work for these so-called electrical synapses, right? So there's fewer of those, right? So if you, so probably still, yeah. So the biggest limiter here, you know, and the fact that we have to get 64 bytes of memory every time we access the memory subsystem, you know, is a problem. And you don't completely get away from that, even if you say I'm going to, you know, put processing in a logic layer underneath a bunch of DRAMs. You know, still have, you know, a minimum. If you want the maximum bandwidth, you're still going to have a minimum access granularity. You know, you really have to do completely different structures where, you know, maybe and these kinds of things have been done also, I think, one out of our Zurich lab, where you have things that look more like you know, flash memory or phase change memory, that kind of stuff, where you know, kind of grow a connection based on activity. You know, that would get to, you know, really thin kind of memory processing.
Thank you.
So I guess it's clear that the future cloud computing and future data center will be heterogeneous, right? So on one hand you have like Amazon that supports, for example, processors with GPUs and FPGAs, and on the other hand you have a Google or Baidu that they have a TensorFlow processing unit, or Baidu has its own AI application specific. So do you think one of these architectures will prevail? So do you think it will prevail GPUs with FPGAs, or do you think that there will be application-specific platforms like TensorFlow processor or AI units?
Well, both is a pretty safe bet, right? So it depends on the context of who is operating, right? So the reason that you might see, you know, certain organizations do this, you know, if you kind of have a captive workload, right, where you know that you're spending a certain amount of your infrastructure on calculating these kinds of things, then it pays off and if you have that at sufficient scale, then it pays off to specialize, right? If a typical problem that we see in supercomputing centers is, we have these very, very highly capable things for certain applications, right? But the number of applications that have been optimized for this kind of an architecture might not yet be very big. So in the past, that usually meant that these kinds of systems would go preferentially into sort of the really high-end kind of things where people can afford to make the software investment to leverage their hardware. What we see now with deep learning is that there is a, because of the things like, TensorFlow, Keras, and even higher level frameworks we did on both our AI vision, where people don't, they just work with images and annotating stuff and all that, and all the other machinery is under the covers. The audience that is able to use these kinds of machines, is growing very fast. So I would say with some confidence that you will see, more adoption of this kind of specialized hardware, even in data centers that you may think serve a fairly generic audience.
Just a quick question. Yeah, okay, thanks for the talk. Okay. Okay, in slide number 7, you mentioned, you mentioned that IBM introduced the custom hardware. Just what kind of custom hardware?
Oh,
this data science conference. What custom is?
It's
also what is just.
Yeah, no, it's like it's not. It is a processing unit, but it's a specialized processing unit, for this kind of AI, right? So it pays attention to, it's very power optimized.
Okay.
It has this.
Just and a quick question is, okay, you mentioned the arithmetic of Gustafson arithmetic. There's a lot of debate about.
Yeah.
Okay. Also discussed before. Okay. I mean, of course, it's not commercially available. There's no about arithmetic units, okay. But what's your feel? Just
yeah, no.
this
I find it interesting enough that you know, in my role at Delft, I've had some students develop you know, FPGA-based POSIT units, right? So that you know, we get about a factor of 1,000 or so speed up over software simulation of POSITs, and hopefully, you know, that would allow more people to you know, to do it. I have another student together with a colleague of mine, Professor Al-Aras, you know, who is looking at the hidden Markov models and then doing it on top of this POSIT hardware, you know, again to see, you know, whether at that scale we actually get a benefit and how much of a benefit. Now, one of the things that I did notice is that definitely some of the benefit can come from these things like fire registers, right? Like the intermediate representation in your dot product, and some of the best benefit comes from the representation. Now one thing that there is one paper, but it's not something I've studied very much myself, is that the symmetry of these posits is really nicer. Right? So when you have things like 10H type you know, transfer functions, you know, it may turn out to be attractive for that kind of thing. But no, this is something we're studying. I'm not up here and saying, okay, this is a done deal. Thank you.
Last question, one.
One for Georgia very nice talk here. So in 2012, when the earlier works from Daniel Moore was coming out, at that point, the timing-based neural network and artificial neural network were sort of at parity, right? Now artificial neural network has sort of made a big jump. Are there applications where timing-based models are outperforming artificial neural network? I'm trying to understand what sort of applications are.
Yeah, I just don't know. Like I said, I'm not a neurobiologist. I'll take your question to heart though, and I'll look at this, right? Because it goes, you know, from an architect's perspective, which is really what I'm trying to do here is to understand which things matter, right? So if that much more detailed model turns out to be fundamental to you know, understanding how this really works, and certainly you know, it's I kind of assumed here, right, that the convolution type stuff was maybe more relevant at the front end, and the fully interconnected stuff was more relevant in the back end. You know, I may not be entirely correct about that either, right? So that back end could evolve into something that has more specialized regions, and then, you know, I don't know. What I know is that there's more to learn. Thank you. Good question.
So you could be there.